Hello everyone, it's me, Mr. Younger. I'm here to teach you how to use some various formulas that we have or that I've introduced for torque, and I'm going to do that with one big example. It can be watched in several little pieces because I'm going to do a sort of separate calculation for each individual torque, and then of course add up the torques to get the net torque. So let's go ahead and share my iPad screen. Okay, so you can see the problem. Basically, the purple sketch is a Greek letter gamma. You can imagine it being installed on a fraternity or a sorority house or something like that. And we have four forces acting on it, F1, F2, F3, and F4. And we're asked what is the total torque on this gamma sign? Uh, I don't know why there's a hyphen there, but anyways, assign clockwise torques negative signs and counterclockwise torques as positive. So that gives us a way to get a final answer without having to specify specifically directions and also to show that, some of the torques are counteracting or fighting the other torques. So hopefully that'll make sense to you as we move along. So let's go ahead and get started. The solution for this, of course, is going to involve It's going to involve some equations for torque. The equations for torque that I've given you are torque, the vector, technically pseudo vector because it's a cross product, is equal to R cross F. And of course, we know that that is also called the vector product in addition to the cross product, and therefore its magnitude, which we can just write as the regular vector with absolute value bars, or you can just write the regular symbol without the vector symbol at all, and that's just the magnitude, and that becomes R times F times the sine of theta. And when you use that, you really need somewhat of a diagram. The diagram that you need is basically a tail-to-tail vector representation of R vector and F vector and theta being the angle between them when they're tail to tail. So that helps you know exactly what I mean by RF sine theta. What is exactly the theta that we're talking about? So this diagram should help you figure that out. I just noticed that my vector symbol on my R did not look very good. It was actually intruding on the space of the torque. So anyways, that's two of the formulas. Some other formulas, though, are torque is equal to the component of the lever arm that's perpendicular to the force. So the component of lever arm perpendicular to the force is R perpendicular, and then we just multiply it by the magnitude of the force. Or alternatively, you can take the component of the force that's perpendicular to the lever arm and just multiply it by the lever arm. And in all these cases, I'll say the lever arm is a vector that points from the axis of rotation to the point of application of the force. So just so everybody's on the same page with that, I'll write it out. The lever arm is a vector. Oops. Evidently I was spelling vector with an F. Is a vector from the axis of rotation, I say axis of potential rotation, to the point of, it's supposed to be of application of the force. So that's the key thing to know. Now we can continue with our solution. I'm going to say torque due to F1. We can see that if we actually pulled on to the right with F1 of 50 newtons, that would tend to rotate this gamma symbol in a clockwise rotation. Therefore, we should call it a negative quantity. And in fact, let's go ahead and draw the actual lever arm vector so that we can decide which formula we're going to use. I am going to draw the lever arm vector in a color. I would like a color that we haven't used. Uh, we haven't used this one much, so I'll take this color pink that's almost red, but not exactly pink, but not exactly red. So the lever arm, as I said, is a vector that points from the center of rotation to the point of application of the force. So it's right there that we call the lever arm vector. And that, of course, is the lever arm vector for F1. Now you can see that that vector breaks up into components parallel and perpendicular to F. So if we wish to do this calculation, all we really have to do is uh, use the formula torque is equal to the component of the lever arm, R perpendicular to the force. So I'm going to use that formula. So all I need is the component of that R that's perpendicular to force. If we look at this vector, we can see that it breaks down into a vector that is parallel to the lever arm, or excuse me, parallel to the force, and a component that's perpendicular to the force. So this vector right here is R perp, and this vector right here, it would be R parallel. And again, that means R parallel to F1, and it means R perpendicular to F1. It might even help to put a 1 as a subscript on it as well. But either way, now we're going to go ahead and calculate that. We can see from the diagram that the component of the vector perpendicular to the force is just extending from the center of axis of rotation to that little short leg of the gamma right here. We can see that it's 4 meters up to here, and then we go back down this distance, which is 1.00 meters. So clearly the component of R that is perpendicular to F is 4 minus 1 meter, which is equal to 3 meters. So we can go ahead and compute that. We're going to say equals 3.00 meters times the force, which is 50.0 newtons. And as we said, this is actually causing a clockwise rotation, which we call negative. So I want to put a negative sign in front of that as well. And we get 3 times 50, and that should be equal to negative 150. And that's 3 sig figs, 350 Newton meters. So again, let me reiterate what we did. The R perpendicular component is this guy right here, but this guy right here ends here. This distance is 4 meters, and then this distance down here is 1 meter, so the R perpendicular was 3 meters. So hopefully that makes some sense to you. And we've got one of our results. Now we got to figure out the torque due to F2. I've actually decided to do this on several pages so that you can see the diagrams with the lever arms without all the complications of having a bunch of different lever arms. So that was the lever arm and torque calculation for F1. Now I'm going to turn to the other page to do F2. So for F2, we can see that our lever arm is going to be from the axis of rotation, excuse me, from the axis of rotation to the point of application of the force, and we can see that that is in fact this lever arm right here. So there's our lever arm. In this case, we can see that our lever arm can be broken up into components parallel to the force, which would be that one, or excuse me, that one's perpendicular to the force. So this would be R perpendicular. and then a component that is parallel to the force, which is this one right here. And this is going to be what we call R perp, or excuse me, R parallel. So we can see now that when we're dealing with force 2, there is a component that is perpendicular to the force. It's that little itty bitty one at the top right here. And then there's one that's parallel to the force, and that's that one. We're not using that one because this force F2 points this way. We need this component. What we see is the whole width from here to here is 2.75. I know this is zero point 0.7 and this is 0.7. So the lever arm, or the R perpendicular for the second force is, torque due to F2, we're going to say R perp is equal to 2.75 meters. Now, again, that is all the way from here to here, or which the force is just right here, so we really only need this little part. I have a measurement from here to here that's 2.75 meters, so all I really have to do is subtract this from it, which is zero point 0.7, and subtract this from it, which is 0.7. So I'll say minus 0.700 meters minus 0.700 meters, and that gives me the component of R perpendicular to F being 2.75 minus 1.4. That would be 1.35 meters. So that torque 2, which by the way does cause a counterclockwise rotation and therefore is positive, is going to be R perpendicular times F. And again, I'm going to put it positive because, as you can tell, if you pulled up right here on this lambda symbol, on this gamma symbol, it would tend to rotate that way. That's why the symbol is positive. So now that we have the component of R that's perpendicular, all I have to do is do the multiplication. The sign is positive. The R perpendicular is 1.35. Just to check, we can take 1.35, add 0.7 to it. That'll give us 2.05, and then add 0.7 again, and that would give us 2.75. So we know that my arithmetic was right. Now the force is actually 40 newtons. So now you've seen how we can use R perpendicular times F. And in this case, we're going to multiply 1.35 times 40. And of course, that gives us 3 sig figs. And it turns out to be positive 54.000 Newton meters for that torque. So I'll underline that one. I'm going to go back and underline the other one too, so it'll be easy for me to find. And now we need to find the force, or excuse me, the torque due to F3. So I'm going to turn to another page so again we can get a clear drawing of the lever arm and the force vector and all that. So let's turn to the next page. So now we're going to draw a vector from the center of the axis of rotation to the point of application of the force, which should be right there. Oops, that was my attempt to let the computer draw it properly and neatly, and it screwed up, but this time it got it right. So here is our actual lever arm vector, which I'll just put R vector this time instead of listing it as lever arm, mainly because I didn't have the room to write lever arm to the left here, and I'm getting ready to draw the components that are in some sense perpendicular or parallel. But in this sense, we see that there's really no easy way of finding R being perpendicular or having a component perpendicular to F, nor is there any easy way of finding F component that's perpendicular to R. So this is a really good chance for us to, for instance, use our RF sine theta equation, for instance. So for instance, we know we could find this angle, and then that angle would actually be, once we add it with the angle between the R vector and the F vector, and then add 30 degrees to that, we would get 90 degrees. So if we were able to actually figure out what this angle right here is, and I'll call it phi, then we could get some vectors and move them tail to tail. So in principle, what I'm saying is if I followed this line out, this would be the angle phi I was referring to. This is the angle theta that is in the formula for torque, which is R times F times sine of theta. And then this 30 degrees added to theta. So let me show you again. This 30 degrees added to this theta added to this phi gives us 90 degrees. So we should be able to figure out exactly what that is. So in an attempt to do that, we're going to say torque due to F3. In this case, I'm using torque 3 is equal to R times F times the sine of theta. But when I do this, I've actually got to figure out what theta is because remember it comes with the diagram where this could be R, this could be F, and this could be the angle theta. So we're going to do all that. First off, I'm going to find out what the angle phi is. And the angle phi, we can see clearly moves to the left by an amount 0.70, and it clearly moves up by an amount 4.00. So the tangent inverse should give a, or the tangent inverse of the opposite side, which is the zero point 0.7 meters, divided by the adjacent side, which is the 4.00 meters. The inverse tangent of that should give us the angle phi. So I'm going to say shift tangent inverse, parentheses, zero point 0.7 divided by 4 in parentheses, gives me 9.926. 9262 degrees. We use 3 sig figs, so in principle we should be able to get 3 sig figs out. I carried 2 extra digits as well. Now what we saw from the diagram that I showed using the laser pointer device was that we had an angle phi, then we had an angle theta, and then we had an angle 30.0 degrees. So what we know is phi plus theta plus 30.0 degrees is equal to 90.0 degrees. We know phi is 9.9262 degrees plus theta plus 30.0 degrees equals 90.0 degrees. So finally we can say theta is equal to 90 minus 30 would be 60, minus 9.9262 is 50.07. That's 74 degrees, and again, that gives us to uh, 3 significant figures. In this case, we're actually adding things that only have 1 decimal place and subtracting things that only had 1 or 2 decimal places. So our ultimate result had to be rounded to 1 decimal place. So I'm keeping the extra 7 just to have extra digits, but we now know what theta is. So finally, we can say the torque due to number 3 is equal to R, which obviously we need to know the actual dimension of it, which I have not worked out yet, but the Pythagorean theorem is going to help us on that one. It's going to be the square root of 0.700 meters squared plus the square of 4.00 meters squared. And of course, like I said, we are taking the square root of that. That's the R. The F, on the other hand, is 20 newtons. We can look up there and see, even though I wrote it kind of small, it is 20 newtons. So I'm going to write times 20.0 newtons, and then I'm going to take the sine of 50.074. I'll leave the units off just for room. But now we can go ahead and calculate all this. It should be careful with the addition going under the square root. So I'm going to take zero point 0.7 and I'm going to square that, and I get 0.49, which means I'm actually good to 3 decimal places. And I'm going to take 4 and I'm going to square that, and that's going to give me 16. And since that had 3 sig figs, that means I'm good to 1 decimal place. So I'm adding the 0.49 and the 1/6, with the 0.49 having 3 decimal places, good to the thousandths place, and the 16 only good to the tenths place. So when I add them, I really only get 1 decimal place. So it's the square root of 16.490, where only the 16.4 part is significant. So I'm going to say square root of 16.490 meters squared times 20.0 newtons times the sine of 50.074 degrees. Now we can do that. I'm going to take the square root of 16.49, and that gives me 4.06. That is 3 sig figs, which is good. I'm going to multiply that by 20, and then we'll multiply that by the sine of 50.074. And again, that is 3 sig figs going in. I've got 3 sig figs in all the factors. This gives me a net torque of 62.282, where the 8 and the 2 are extra digits, and that is in Newton meters. And technically, I haven't discussed whether that is a clockwise or counterclockwise torque. Hopefully, I've already figured that out, but clearly, if I'm pulling this way, it's going to try to lift it, but basically it's still turning in that counterclockwise direction. So I just need to put a plus symbol by it because it is positive, and we're going to underline it. Now that is a good way, and it certainly got me the right answer, but there's another way that might even be in some sense easier, and it's just going to involve me uh, putting in a coordinate system just for us to have a coordinate system. So let's imagine if I put the origin right there at the axis of rotation, so that now the x-axis is right here and the y-axis is right there going along the edge of the actual lambda. I drew a little gap just so you could see it, but really it should be exactly in the same spot, and the x-axis should be exactly lined up with the bottom of the Greek letter gamma there. So now that we have that, let's make our vector. So we can, for instance, go ahead and use an alternative version. The alternative version is our alternative method. We're going to use torque is equal to R cross F, which involves a cross product and a determinant. So I wanted to make sure I have an example for you guys done this way, even though we have done them in class before, and I do have various videos of me calculating determinants. But right here, I think you all can see that it's pretty straightforward to write the vector R hat, or excuse me, R vector, as having a y component that is 4 meters and a x component that is negative 0.7 meters. So I'm going to say negative 0.700 meters times I hat plus 4.00 meters times j hat. That's our R vector. And then our F vector, since it happens to be a 30-degree triangle, we might recall, for instance, that if you had a triangle that was 30 degrees, oops, that was not looking very good. If you had a triangle that was 30 degrees, like this, then the opposite angle was the smaller side, which was 1. The longer side was the square root of 3, and the hypotenuse was 2. And then this angle over here is 60 degrees. So what we can tell is that this is normally a multiple of 2, but in our case, we actually had 20, so I have to multiply by 3, or excuse me, by 10 on all these things. So this one's going to become 2 times 10. This one's going to become about 1.732 times 10, and this one's going to become 1 times 10. So now I can actually use that to find the components of the force. Again, you could just use your trig functions, take the cosine to find a component of F that is actually horizontal by just multiplying 20 newtons times cosine 30, and then you could find a component that's vertical by taking 20 newtons times the sine of 30. That works fine as well. We just have to remember our sines. But what I'm going to do is go ahead and use this result that I did from remembering my special triangle. So the F will actually have obviously a positive y component because it goes up and the y-axis points up, and it has a negative x component because it goes to the left and the positive x-axis goes to the right. So all I have to do is say, okay, well, the equivalent of that 20 Newton vector is this 20 Newton vector that has 1.732 as its x component times 10, and it has 10 as its y component. So the x component is going to be a negative 17.320. And actually, I don't know what's after the 2 and the square root of 3, but let me check real quick just to make sure. Let's do square root 1.732. Actually, 7321. So I guess it's 5 is the next digit. So I'd put a 1 there. So that's 17.32 newtons. That's the x component. So I write it with I hat. And then the y component is going to be 1 times 10. So, and it will be positive. So that's 10.000 newtons in the j hat direction. So now we have R and J as vectors in IJK notation. R cross F, the torque, is the determinant of a matrix. And if you actually write a matrix with absolute value bars instead of bent ones, that's sort of understood automatically to be the determinant. So I can just write I hat, J hat, and K hat as my first row. My second row is going to be R, the first vector in the cross product, and we see that that's negative 0.7 is the x component. Again, we got 3 sig figs totals, but we're not going to waste all the space in here. We got 4.0 0, technically for the y component, and then we got 0 for the k component. And then for the force, we got negative 17.321 for the x component, and 10 for the y component, and 0 for the z component. Now, the way that we teach this usually in the physics class is we imagine expanding this determinant along this row. So we start off using this I hat, and then we use J hat, and then we use K hat. And the way that works is when you choose to expand it in terms of I hat, you take the I hat, and then that eliminates that row and that column, so that all you're left with is this little matrix over here. And you have to take and write the I hat, and then write -1 to a power. Specifically, the power is the row and column number of the I hat added together, and then do the determinant of the remaining matrix, which is this guy, and you do 4.0 times 0 minus 0 times 10. That's the actual determinant. So that's what we're going to do. I'm going to say equals I hat. And then just to remind you what we're talking about, you put in parentheses a -1, and then you'll notice that the row number for the I hat is 1, and the column number is also 1. So we're raising this to the 1 plus 1 power, which of course means nothing, because 1 plus 1 is 2, -1 to the 2 is just +1, so we're just multiplying by 1. No big deal on that one. However, the next one, when we do J, that's 1, 2, and when we do K, that's 1, 3. But the 1, 2 is 1 plus 2 is 3. When you raise a -1 to a third power, you get a -1. So we actually have to deal with it then. But right now, all we're left with is we've done the I hat part, we've done the multiplier part. Now we have to take the determinant of what is left, which is this matrix right here. And generally, 2 by 2 matrix, the determinant is top left times bottom right minus top right times bottom left. So we're going to go 4.0 times 0 minus 0 times 10. So all I have to do is write right here 4 times 0 minus 0 times 10. I'm not even going to put the units on there specifically because we know that the result came out to be 0. I'm also going to do the j hat term now. Remember, we actually got to do each of those in turn, so we're getting a sum here. So we just did the I hat. Now we're doing the j hat. Now the j hat has a 1, 3 subscript, or excuse me, a 1, 2 subscript, which means 1 plus 2 is 3, and that gives us a negative number. Rather than me just writing a negative, what I normally do is go ahead and realize I am using j. That means this row and this column are no longer valid. That means my matrix includes these two guys and these two guys. Now normally this 2 by 2 matrix would require me to do -7.0 times 0 and then 0 minus 0 times -17.321. But since the j has a -1 that has to be multiplied by it, I'm going to do it in the opposite order. That's how I do it. It's completely up to you what you want to do. So I don't even write the -1 to a power. I only did that in the first one to show you what I was talking about. I just go ahead and put my square brackets up here. And what I'm going to do is take 0 times -17.321 minus, now I'm going to do -0.7 times 0. And again, you see that's just 0. And finally, I got one more term, and that's the k hat term. And of course the k hat term, again, we're expanding upon the k hat. That means there's our k hat. This column and this row are eliminated. That means all we're left with is this, and the 1 plus 3 is 4. -1 to the 4 power is positive 1, so we don't need to do anything with that. So all I have to do now is take the determinant of this by multiplying -0.7 times 10 minus 4.0 times -17.32. In doing that, we're going to get the following results. So we're going to say -0.7 times 10 minus 4.0 times -17.321. And you can see both the terms came out to be 0 except for the k. So now I have torque as a vector quantity is just equal to some number times k hat. 0.7 times 10, or actually -0.7 times 10 is -7. So I get -7 for the first part of that. And then negative times a negative is going to give us a positive. So 4 times 17.321, 4 times 17.321 is 69.284. So I'm going to have -7.00 Newton meters, and then minus and minus gave me a positive, and that gave me 69.284 Newton meters, and all that will be times K hat, so that we can find torque is equal to 62.284. And it does turn out to be positive, which means the net torque is actually in a counterclockwise direction, but 62.284 with two extra non-significant digits, Newton meters, which you can see at least to the proper number of significant figures, and even one more, it's actually exactly the same answer we got before. So that's how you can do it with an actual determinant. Again, look on my YouTube channel for determinants, do a search for determinant, or do a search for cross products, and you'll see plenty of examples of that. So now we've done torque 1, torque 2, and torque 3. We only have torque 4 left, and we even did torque 3 two different ways. So now let's address torque 4. So torque due to 4. So in this case, we can do again all the various formulas, but in this case, this one's kind of nice in that it's probably really easy for me to take the component of the force that's perpendicular to the lever arm. So I'm going to use F perpendicular times R is equal to the torque. And I will mention that the way this one's pulling, this one tends to rotate it in a counterclockwise direction, so that is actually a positive torque. So what I want to show you first off is that this vector right here is the lever arm. And you can see obviously that the force vector actually has a component that is parallel to the lever arm, that's F parallel, and then it has another component that is perpendicular to the lever arm, that's F perpendicular. And knowing that that special angle 53.1 is there, we can automatically see that what we have is a 3-4-5 triangle where this is 5 times 5, or let's say 5 times 5.00 newtons, and this is 53.1 degrees, and that means this is 4.0, or excuse me, it should be 4 times 5, so it's going to be 4 times 5.00 newtons, and this one's going to be 3 times 5.00 newtons. And that helps us immensely because we can see that the x component is negative, the y component is negative, and their components are actually 15 and 20. So I can immediately just write out that the component of F that is perpendicular to the lever arm is the 20 newtons. And then the lever arm itself is just the length 0.700 meters, and that should give us 20 times 0.7 would be the same thing as 2 times 7, which should be 14.000 Newton meters. And that's our torque 4. So now what we have, continuing, the torque total is equal to the summation from I equals 1 to N, which in this case N is equal to 4, of torque sub I. So what we see in the first result, we got 54.000. So I have 54.000 Newton meters plus the second one. The second torque, we got 50, that was the second torque. Oops, 54. Oh, we missed the first one. The first one's negative 150. So let's kill this. Say it's negative 150.00 Newton meters. That's the torque due to 1 plus 54.000 Newton meters. That's the torque due to 2. Now the torque due to 3 we found twice was 62.282 or 62.284. So I'm going to call it 62.283 Newton meters, reminding us that the last two are not significant anyways, and I just did split center between them. I should make sure that's actually positive, and it was, and the other one was positive as well, and the previous one was negative, so I've got negatives and two positives, and that looks right. And then finally, we've got the fourth torque, which is the positive 14.00 Newton meters, so that the net torque is actually equal to negative 150 plus 54 plus 62.283 plus, oops, plus 14. And that gives me negative 19.717 Newton meters is the net torque. Now, that's basically a way to do it, but this was very much an instructive problem. The whole purpose of it, of course, was to teach you how to use the various versions of the torque formulas, which included torque as a pseudo vector is equal to R cross F, torque as the magnitude of a pseudovector called the vector product is R times F times the sine of theta, where theta is the angle between R and F, and in this case, you usually use a right-hand rule to decide what the direction the vector force or the vector torque would be. Again, it's really a pseudovector. Look at your section in your book about pseudovectors and rotational vectors and that sort of thing. We also had the formula torque is equal to R perpendicular times F, and we had the formula F perpendicular times R. And in this one problem, we were able to show all of them being used. I hope that helps. And we're going to go ahead and call it. So have a good day.